everyone, it is I, Miss Jemitz, and I'm here to just talk, a little bit about a particular topic in thermodynamics, green energy and chemistry. So in the grade 12 University Prep Chemistry curriculum for Ontario, there's supposed to be a lesson in the thermodynamics unit on green energy. And while we will get to that, I'm going to take it in a slightly different direction and have a bit of a broader conversation first. So the way that the curriculum is set up is that we came from Unit 4, which is on chemical bonding, and we're going to end up in Unit 6, which is chemical kinetics. But from chemical bonding, we made our way into discussions about heat and enthalpy. So what kind of energy is released or absorbed when bonds are broken, and when bonds are made. And then from there, we brought that into a discussion about, chemical equations and how much energy is going to be absorbed or released in a particular process. And if you want to represent the actual energy that is absorbed or released, which side of the equation, the chemical equation, do you put that on if you want to represent it as a term in that equation? Then we moved on to calorimetry, so actually measuring the heat that is absorbed or released, and then into Hess's law, which is where if we can't or we don't necessarily want to record things using calorimetry, you can use an additive process known as Hess's law in order to determine the enthalpy of a particular reaction. Then we talked about enthalpy of formation, which is the true power of Hess's law. And so going from these kind of standard equations where things in their lowest energy form at standard ambient temperature and pressure, the energy that it takes to make a particular compound. So for example, to make magnesium sulfate, you would go from solid magnesium, solid sulfur, and gaseous oxygen, because those are the standard states of magnesium, sulfur, and oxygen. And from here, we're going to go into chemical kinetics. But like I said before, we're going to have a little bit of a different conversation, one a little bit more oriented toward the environment. So in terms of energy, we've talked a lot about the actual energy involved in making and breaking those bonds, in those chemical reactions. And that's not all that there is to it. I mean, we've seen this before. We use this in a Hess's law question. All of these different species, I've got some oxygen, some nitrogen gases, NO and NO2, and we know from the Hess's law question, it's a really common one that's used even in other classes. We know that NO is a short-lived species. It immediately reacts to form NO2 or other things. And so we would have all these processes going on, and we can determine the amount of energy that it takes for each one to happen, what kind of heat is absorbed or released. However, in order for reactions to go, we're not only concerned about what's going on with the actual making and breaking of bonds, but rather the energy that it takes to get to that point. So for a lot of reactions, they need to be either heated or cooled. A lot of them need to be stirred. Maybe they need to go through like several separation processes in order to get a pure product. There's a ton of energy that's involved in each of those steps. And you can think about on an industrial scale what that would look like. So look around the room that you're in. If you have anything that is dyed, paints, anything, chemical engineer was involved at some point in that process. If you're wearing synthetic fabrics like polyester or nylon, chemical engineer was involved, or a chemist. Same thing with plastics, same thing with pretty much anything synthetic or colored. It's a chemical process. Right now it's 2020, and so people are buying just insane amounts of disposable masks, PPE, so protective equipment like gloves or gowns. They're buying hand sanitizer in huge amounts, and they're buying household cleaners to keep everybody safe. And all of those, think about the volume that just your household buys, think about what the hospital buys, think about what the clinics buy, think about what everybody else is buying, and there's just these massive amounts of chemical products that need to be made in order to meet that demand. And all of that takes energy input. Obviously, this is very costly, or it can get very costly. And so industry has a real interest in keeping costs down and keeping that energy input low. But there is another reason to keep that energy low. These are the principles of green chemistry. There are 12 of them. And there is an optional video to watch, a Yale intro to green chemistry, to the 12 principles, that'll link down below. However, you can see all through a lot of them, it's talked about like the actual chemical composition and what are you using and its effect on the environment. But we're just going to focus in on this one, design for energy efficiency. So if we can get a reaction that doesn't need to be heated, doesn't need to be cooled, maybe it needs minimal stirring and it doesn't have to go through a whole bunch of refinement processes, then that's going to minimize the energy input that we need to put into the process in order to get a good, useful final product. Closely related to that is catalysis. Now, this is a little bit more of a conversation for the kinetics unit, but just know in its simplest form that catalysis is one way, a really, really good way to achieve that room temperature, high yield, very, very useful reaction that we're looking for in the principle of design for energy efficiency. So there are a bunch of different ways to minimize the energy input that you need, but I figured, for a little bit of fun, let's talk about some really dramatically different ones. So when you think about chemical synthesis, you probably think about, boiling beakers. And that is the traditional way. We call it solvothermal synthesis. Solvo, meaning there's a lot of solvent and your reagents are dissolved in them. And thermal, because you're heating it, bubbling beakers, And so the bulk of chemistry historically in a lab has been done this way. You take your reagents, you dissolve them in some kind of solvent, sometimes water, usually not, and then you heat the bejesus out of it until it's done a day or 2 or 3 or however many later. And just that entire process with stirring, with reflux, with all sorts of different things, with constant monitoring, it takes a lot of energy, both researcher and electrical or fuel. So a couple of different solid state synthesis methods are mechanochemical synthesis and accelerated aging. So solid state, you've got solid reagents, not dissolved in anything, just powders and rocks, and they become something different. So mechanical chemical synthesis is super simple. It's just grinding things until they react. And you might think if you cook or if you bake or if you've ever been enlisted into, grinding poppy seeds or nuts or corn to make things in the kitchen, that it's possible to take, big particle and break it down into, small particle. That's a physical process in most cases. You're not actually changing the composition of it. You're just breaking it into smaller pieces. However, it is possible, believe it or not, just from grinding something in order to get chemical bonds to break and form. And while this is kind of a trendy, newer, let's write a bunch of papers on, mechanochemical synthesis, this is actually an incredibly old technology. Theophrastus, one of the followers of Aristotle way back in ancient Greece, he recorded the first known instance of a mechanochemical synthesis. He noted that if you took cinnabar, which is a mineral that contains mercury in an ionic form, and you grind it with a little bit of vinegar in a copper bowl, then you'll actually be able to get out liquid quicksilver, so liquid mercury. Obviously, that particular reaction isn't super environmentally friendly, but just sitting there and grinding by hand requires a lot less energy than an entire days-long synthesis in the lab by solvothermal means. So obviously there are better ways. There are different methods that have been developed to actually be used in either a lab on like a very small scale or in industry on a much larger like gram or a kilogram scale. But the general idea behind a mortar and pestle, where you just got something that grinds something up, that still holds and it works. It takes minutes, maybe hours, maybe a day or 2, depending on what you want to do. Accelerated aging, on the other hand, is a very long-term process. It can take, it is measured in days, certainly, or potentially even in weeks. However, all you have to do in order to get it going, and I have here just like, a little converted oven that's been turned into a hydration chamber, is you turn up the heat a little bit. Depending on what time of year you're watching this or where you are in the world, maybe maybe you could even just have it outside, like that temperature. It's nothing too inaccessible. It's nothing crazy. And you add a little bit of water to create this like humid, hydrated atmosphere. And then you put your powders in there that have been, mixed together, homogenized, and they'll react and you can get an actual product out of it. And this is, I mean, it's slow, kind of like solvothermosynthesis or even slower than that, but the energy input is just so little relative to solvothermosynthesis that this is still a really great way of getting products in the solid state. And this process actually is inspired by and mimics geological processes. So how do you get your different kinds of stone out in the earth? And so it's really cool. These are a couple of examples of, taking inspiration from, the past or from nature, from other sources in order to do useful chemistry. However, beyond actually the energy that you have to put in order to get a reaction to go, you have to consider where that energy is coming from. What fuel or what kind of electricity is it? And so if you've got a nice renewable source of energy, then okay, maybe it is pretty green. But if you're going off of, natural gas or coal, maybe it's a little bit less so. So here's just a brief array. I don't have all of them, obviously, just a few that I kind of want to touch on. So you've got coal and that big, ugly plume of black smoke from a coal-powered train. You've got natural gas down at the bottom. You've got solar and wind and hydroelectric. In most cases, all that you want in order to generate this electricity is you need electrons to flow. So most of them use magnets and turbines in order to achieve this. Solar power, it's literally just using the sun to get things to flow. There's no turbine involved. But in all of those cases, the environmental footprint, the environmental impact can be quite different. And you really do need to consider the impact of the energy that you are using as a fledgling chemist and as, just a normal citizen. To end off this little discussion, I want to bring things back around. So we started off talking about, the energy of a chemical reaction, those bonds breaking and forming, and what is associated with that, enthalpy and heat in our grade 12 curriculum. Then we talked about how, we get energy from some kind of input, and we can just kind of carefully tune things, or you can move to something really dramatically different like mechanical synthesis or accelerated aging. Then we talked about, maybe less so for mechanical synthesis with a mortar and pestle, but if you're going to be putting in any kind of energy, you want to consider where that energy is coming from. And is it green? Is it renewable? What kind of environmental impact does it have? And as it just so happens to turn out is that chemical processes and chemical research and design can be used to make those processes better and to make them more green. And I want to just briefly touch on a few of those technologies that chemists are working on in order to improve the way that energy is created, or not created, but generated in our power plants. So first is clean coal, clean in quotes. So maybe this is a little bit less, current. I know it was in the news quite a bit a few years ago, around 2016, 2017. But the idea behind clean coal or natural gas is that you have a material that is really, really good at taking carbon dioxide out of the atmosphere. And so in our top part of this figure, we've got a mixture of gases that's going to go through this CO2 capture material. And guess what? All of the carbon dioxide isn't going to flow out. It's going to be stuck in the material, but everything else is going to be able to go through. So this can either happen before you burn the fuel or after, before it comes out of the smokestacks in a traditional fossil fuel power plant. And sometimes that capture material is the final home of carbon dioxide. It just stops, and then we take our material and we put it in storage forever. Or in some cases, that capture material needs to be good at releasing that carbon dioxide in order to be stored more permanently in a cheaper, better material for that purpose. Again, it doesn't disappear, it doesn't go nowhere, there's still carbon dioxide hanging around. It's just not in the atmosphere, which I guess is better. And so designing those materials, both the capture material and the storage material, comes down to chemists. Next is solar power. And so you can imagine that if we're going to take sun energy and cause it to make electrons flow, that doesn't normally happen. So we have to design a material in order to get that, get the electrons flowing. And traditionally this has been done with thin film inorganic semiconductors like cadmium telluride, CDTE. But one that's kind of interest is a hybrid organic inorganic perovskite. So perovskites, named after the geologist Perovsky, they're just a type of mineral that exists in nature. And chemists do this a lot. They see something that exists in nature, especially minerals, and they go, oh, well, this other thing has a similar structure. We're going to give it the same name, or we're going to give it a similar name. In fact, one of the materials that's commonly used in CO2 scrubbing or separation is known as zeolites, or a slightly different version that you can make in the lab would be with a similar structure is called zeolitic imidazolate frameworks. But you can see zeolite, zeolitic, perovskite, and then you can make your own custom perovskite. They didn't go with perovskitic, I guess. Probably a good call. Anyway, you can see here that it's a combination of an organic cation, a halide anion, so group 17 of your periodic table, and a metal cation that sits in the middle of 8 octahedral halides. So that's the general structure of it. There's all sorts of things that you can do to swap out different A+, X-, M+, like all sorts of different arrangements. But in all cases, they look kind of like a perovskite, and they're good at being solar semiconductors, and they're of great interest. And finally, if we're generating all of this renewable energy, it's not going to be produced uniformly, and it's not going to be used uniformly. So in a normal power plant, they can ramp up production when there's more power needed, and they can kind of slow down production and burn fewer fuels when there's less energy that is needed. However, we can't do that with the sun, and we can't do that with the wind. We're kind of at nature's mercy. And so in order to make this more useful year-round, throughout the entire day-night cycle in all areas of the world, we need to develop really good batteries, really good, cheap, abundant, not very environmentally impactful batteries. And lithium is kind of the gold standard right now, but lithium is really expensive. So sodium, which is like the 4th most abundant element on Earth, is a potential alternative. You can see in your group 1, sodium is right below lithium. And so looking at these solid state sodium ion batteries is something that chemists are really doing lately. So that's all that I have for right now. Hopefully you found it kind of interesting. Check out the links in the description, and have a great day.